Hello, everybody. Let's close the morning with our last talk. It is a pleasure to introduce José Burgos from ICMAT and CSIC in Madrid. So he's going to tell us something about Chern-Weil theory and Hilbert Samuel theorems for semi-positive singular toroidal metrics. Please, floor is yours.
Okay, so first I want to thank the organizer for organizing this conference and this course. It is my first time here in Brazil, and I am delighted to be here, so thank you for organizing this. So what I want to talk today is joint work with Ana Botero, that is here, and David Holmes and Robin de Jong. So I want, in some sense, to talk about a very concrete problem, which are to study Siegel-Jacobi modular forms. And I want to use techniques that, although they don't look like tropical, they are inspired in tropical geometry, and how to use these techniques to get results in this concrete situation. So let me start explaining what are the Siegel-Jacobi modular forms. So I imagine that all of you know what are modular forms. So modular forms will be holomorphic functions defined in the upper half plane that satisfy a cocycle condition. So they are functions that are not periodic with respect to the SL2 set, but they satisfy a cocycle condition. And also they satisfy some boundedness condition on cusps, so some conditions on the Fourier expansion on the cusps. And we can see that since they have this cocycle condition with respect to SL2 set, we can think of them as some kind of generalized functions on the quotient. The quotient by SL2 set will be the modular curve. So we can think that modular forms are sections of a line bundle on a modular curve. Now we can go to higher dimensions and we can look at Siegel modular forms. Then Siegel modular forms will be the same, will be holomorphic functions that now they live in the Siegel upper half space, which is a set of all complex G by G matrices that are symmetric and that have positive imaginary part. And you can also ask for a cocycle condition, but now not with respect to SL2 set, but with respect to the symplectic group. And then also some boundedness condition on the cusps. And then what you get are sections of line bundles on the moduli space of polarized abelian varieties. Then Siegel-Jacobi modular forms will be now, instead of trying to study the moduli space of principally polarized abelian varieties, I want to study the universal family of abelian varieties over the moduli space. And I want to have sections of line bundles on this moduli space of, so the universal family of abelian varieties over the moduli space. So for instance, I can get the zeta functions that gives me embeddings of abelian varieties on projective spaces. There will be examples of Jacobi forms when I see of them in families of abelian varieties. Okay, let me recall a little bit the construction. I will be very brief because in some sense the details are not important for today, but remember that the symplectic group are the set of matrices that respect the symplectic inner product, and they can be written in block form as matrices A, B, C, D, such that A transpose times C is equal to C transpose times A, and so on. There are these conditions, and these live in GL2 G set. Then we always can embed a symplectic group inside a bigger symplectic group. So I can, just by adding ones here and here, then I can embed the symplectic group in a bigger group. Now I can also look at the Heisenberg group. The Heisenberg group is an extension of a lattice. So here I have a lattice lambda mu, and I add a scalar here. And I can tell you what is the group action just by telling you how I can embed the Heisenberg group inside the symplectic group. So now I embed it as this row here and this column here. Okay? Now, when having this embedding, then I can see the product will be just product multiplication. Now you see that I have two groups, the symplectic group and the Heisenberg group, and both are in the same big group, which means that I can automatically construct the semi-direct product of these two groups just by using the operation in the big group. So the Jacobi group will be just the semi-direct product of this symplectic group and this group here. Observe that this group here is a lattice with a little bit more. And you know that an abelian variety can be written as a vector space divided out by a lattice. So it makes sense that this will be related with the universal family of abelian varieties.
Professor, Heisenberg group is normalized by the
Yes. And now what is the action of the Jacobi group? So now I take again the Siegel upper half space. Then the Jacobi group acts on the product of the Siegel upper half space times CG as follows. So if I have a symplectic matrix and an element of the Heisenberg group and a point in CG, then the action of M times L mu X on set W is, here we have the usual action of the symplectic group on the upper half space, and on the other part we have just the action by the lattice. You see that the lattice is changing, so in every point set of the upper half space I am considering a different lattice, so the W is moving by a different lattice, and then one also have to multiply by this term to get a good action. And then the quotient of AG cross C to the G by this group is exactly the universal abelian, the universal stack of principally polarized abelian varieties. And if one don't want to work with the stacks, instead of considering the whole symplectic group, one can consider a subgroup with finite index that is neat. Okay, so this is the space. Now the Siegel-Jacobi modular forms. Now we will use more or less the same recipe. So we want to consider functions that lives in the product of the upper half space times C to the G. But now we want that they satisfy two co-cycle conditions. So for symplectic matrices, I want to satisfy this condition. The first part is the usual condition that appears in Siegel upper half space, and the second one depends on this index M. Now I have also to explain how it moves with respect to the Heisenberg part, and this is the co-cycle condition. What is important to remember of this slide is that in contrast with Siegel modular forms that gives me a graded object, only 1 degree, which is the weight, here I have 2 degrees, the weight K and the index M. So Siegel-Jacobi form have 2 degrees, the weight and the index, K and M. And K tells me how it changes with respect to the symplectic group, and the index mainly tells me how it acts, so how it changes with respect to the lattice. And also I will need another condition about the Fourier transform. Now the point is that a Siegel modular form can admit a Fourier expansion, but now instead of having numbers as indexes, so the index are given by matrices. So every time I have a matrix, I can define a function which is exponential of, essentially the exponential of the trace of t times c. This will give me a function. Whenever I have a row vector, I can get also a function like this. And any Siegel-Jacobi modular form will have an expansion like this. And then I want to impose that not all coefficients will be non-zero, but only positive ones. So only when this matrix here is semi-positive definite, I can have a non-zero coefficient. So it's a little bit like in modular forms, that you don't want your expansion to be a Laurent expansion, you want really to be a series starting with 0, in order not to have poles at infinity. And then we can also talk about the Kocher principle and cast forms. So the Kocher principle tells me that if the genus is bigger than 2, if G is bigger or equal than 2, the third condition is not necessary, it's automatic. So whenever I have any function that satisfies condition 1 and 2, then it always will satisfy condition 3. This is not true in the case of genus 1. And in the case of the Siegel upper half space, this is explained by the existence of the Satake compactification. So we know that the modular space of principally polarized abelian varieties admits a compactification, the Satake compactification, with a very high codimension on the boundary. And since it has very high codimension on the boundary, there is no way I can have poles on the boundary, because the boundary has a very high codimension. So which means that every time I have a function in the interior, it will not have a poles in the boundary. But this is not true for genus 1. And in this case, we have a similar result. So if genus is bigger or equal than 2, there is no need to impose conditional. And we can also define cusp forms, and the cusp forms will be the forms that satisfy some extra vanishing condition. In this case, I will ask that the coefficients in the Fourier expansion, the non-zero coefficients, not only I ask that this matrix was semi-positive definite, but I ask that it is really positive definite, which means that several coefficients will be 0 at the boundary. It's like in the case of modular forms, a modular form is a cusp modular form, is the 0 coefficient is also 0. So if it has a leading coefficient equal to 0. Okay. Now, since, yes? What? Well, this will be part of my talk. Then the line bundle of Seeger-Jacobi forms. Now I consider a neat subgroup just of finite index, just to avoid using stacks. And then I will write AG of gamma will be the quotient of the upper half space by the group gamma. UG of gamma will be the quotient of AG cross CG by this Heisenberg group. This will be the universal family of abelian varieties over this modular variety. And then conditions 1 and 2 will define a cocycle for this group. And hence, it will define a line bundle on the question. Okay? And now, sections of this line bundle will be the Siegel-Jacobi forms of weight k and index m. We'll be writing like this. And we have then this inclusion. So Jacobi forms will be sections of this line bundle. And the Köcher principle tells me that this is an equality if G is bigger or equal than 2. That all sections, that all Jacobi forms are sections of this bundle. Okay? Now, this is a ring because I can multiply Jacobi forms and they will be again a Jacobi form. And it is a bigger ring because the weight is additive and the index is additive. So we can ask a lot of questions about the ring. So for instance, the first question, if you have a new ring that you don't know anything about, the first thing you can ask is it finitely generated? Because if it is finitely generated, it will be easy to work with. But it is easy to see that if I take the ring of all Jacobi forms, this ring will never be finitely generated. And this is easy to see because if I consider the Jacobi form of weight 0 and index m, with m positive, then there are none. So there is no Jacobi form of weight 0 and height index. But if I fix weight, let's say a big enough weight, and then I take all possible m, then there are Jacobi forms for all possible big enough m's. And then it's like looking now at an open cone. It can never be finitely generated because, so we have the picture will be something like this. So I have something in 0, 0, then here there is nothing, but then there are something on all these lines. So if it is finitely generated, this means that at some point I will not have more generators, and then I cannot obtain these points here. So it is clear that the whole ring cannot be finitely generated. But then one can ask, okay, now let's fix k and m. So I want to look at an array on this graded object. So I fix k and m, and then I look at all possible multiples, j, lk, lm of gamma. This is again a ring, and now I can ask whether this ring is finitely generated. The fact that this is finitely generated is, in some sense, is very tempting because if I had a Satake type compactification in such a way that this j, lk, lm extend to some ample line bundle, then I will get that this guy is finitely generated. And and in some sense, this will explain the Köcher principle. Okay, so it's very tempting that this is the case. And in fact, in the 90s last century, so it was believed that it was finitely generated. So there is a paper that states that it is finitely generated, and it has been used, the fact that this ring is finitely generated. But a theorem that we prove with Anna is that, in fact, it is not true. So it is not finitely generated for any k and m. Okay, more questions we can ask. Okay, the next question we can ask is, what is the dimension of, yes?
Perhaps I missed something, so they did not prove, right?
Eh?
How they just state.
So what I'm saying is that it's not true.
It's not correct.
Yes. Yeah?
I also have a question. Maybe I missed it. How do you elements in J sub Km? How does the grading behave with multiplication?
It is a graded ring in the sense that if you look at the cocycle condition, if you take two elements, one satisfies the cocycle condition for Km, another one satisfies the cocycle condition for K prime M prime, and you multiply, then you will get that it satisfies the cocycle condition for K plus K prime and M plus M prime. So it is really a big graded ring.
Okay. Thank you.
Yeah. You're welcome. Okay. So one natural question is to compute these dimensions. But this is a very difficult question, so we can just settle to compute the asymptotic growth of this section. So we can look at what is the limb sup when L goes to infinity of the dimension of J, Lk, Lm, and then divided by L to the d factorial. Well, here, the d is the dimension of the universal family, which here you can see the dimension of the moduli space of abelian varieties, and G is the dimension of the abelian variety. So D is the total dimension. This question was already answered by Tai in 82, and it's a combinatorial formula that depends on the Bernoulli numbers, the index of the neat subgroup you are considering, and then some stuff that has to do with the index and the weight. Okay. But one question that maybe remains is whether we can give an intersection theoretical interpretation to this dimension. Because, for instance, if I look at the case of modular Siegel modular forms, then the dimension, the growth of the dimension of the space of modular forms is given by the degree of the line bundle of modular forms, which is this degree can be seen as a self-intersection product of the divisor associated to this degree. Okay? Yes.
Kind of looks like asymptotic Riemann graph or Hilbert.
Yeah, Hilbert Samuel. This is why Hilbert Samuel was in the title of my talk, because I want to prove some kind of Hilbert Samuel result. Yeah, exactly. And the point is, the answer that we will see, making some spoilers, is that yes, we can get an intersection theoretical explanation, but not really as an intersection of divisors. We will need to do an intersection of what we can call B divisors, which are birational divisors that I will explain more later on. Okay? Okay. And the key point, so the key object that we will use is the invariant metric. So this line bundle is not just the line bundle of Jacobi forms. It's not a line bundle. It's a line bundle that comes equipped with a very natural metric. The natural metric is can be written explicitly as follows. So the norm of f, here I am seeing f as a section of the line bundle. In the right, f is the function. It's a function on the upper half space. So then the norm of f as a section will be the absolute value of the function, and then multiply by the determinant of y to the k, and this exponential that depends on beta and y, where the point set is x plus iy, and w is alpha plus I beta. And now one can prove easily that if f satisfies the cocycle condition, then this function is Rayleigh periodic. And since this function is Rayleigh periodic, this gives me a function on the base, and hence is a well-defined norm of the section f. Okay? And this has also a group theoretical interpretation in the sense that is the canonical invariant metric. And there is a theorem by Ziegler that tells me that a holomorphic section of the line bundle of Jacobi forms, Km, on the universal family of abelian varieties, it is a cusp Siegel-Jacobi form if and only if this norm is bounded. Okay? Analogously, one can look what will be the Siegel-Jacobi forms. The Siegel-Jacobi forms will be those that this norm is not necessarily bounded, but has only logarithmic growth at most. Okay, but if it is bounded, then it is cusp Siegel-Jacobi form. So this theorem is what links, in some sense, the Jacobi forms with this metric. So this metric really tells you which are the Siegel-Jacobi forms. Okay. Now, the question is that so the universal family of abelian varieties, there is all this theory of toroidal compactifications. I can look at a toroidal compactification of the universal family of abelian varieties. I have a line bundle on the open. This line bundle has a norm. Then the first thing is to say, okay, can I extend the line bundle to a line bundle on the ambient space such as the norm, for instance, extends continuously? And the answer is no. So this invariant metric does not extend smoothly to a toroidal compactification, and it has singularities that they are even worse of log-log singularities, so it's an interesting the kind of singularities. But what is true is that when K and M are bigger, then this metric is semi-positive. It's what we can call a plurisubharmonic metric on the space, and it is toroidal in the sense that the singularities really are toroidal. They are not arbitrary singularities. I will come back to what are toroidal singularities. So the key point to keep in mind of all this process is that I have a quasi-projective variety, this universal family of abelian varieties. On this quasi-projective variety, I have a big-graded family of line bundles. And these line bundles have a metric. And the important thing is that the metric does not extend to something smooth on the space, but it extends to something plurisubharmonic on the space, so positive on the space. So this is important. And the singularities are very mild. They are toroidal. That will mean what this means.
So there's
Yes?
toroidal compactification
Yeah.
for all K and M, or?
No, so there is a toroidal compactification of the universal space. And now the line bundle lives in the open part. And then, of course, you can see the open part as open part of any toroidal compactification for all K and M, but I cannot, for the moment, I cannot extend the line bundle. Yeah, but then so in any toroidal compactification, the line bundle will extend to a line bundle with a PSH metric. Okay? But to many line bundles with a PSH metric. So the point is that if you have a line bundle with a plurisubharmonic metric, you can tensor with yeah. So in some sense, the extension as a line bundle in the compactification is not unique. So there are many possible extensions.
But I was wondering if this toroidal compactification depends on K and M.
No. The toroidal is a toroidal compactification of the space.
There are many.
Exactly. And you can take whatever the one you prefer. So you can take any toroidal compactification.
For any toroidal
Yes.
compactification?
Yes. That's the point. Yeah. Now I want to recall a little bit about the Chern-Weil theory and the Hilbert Samuel theorem that we want to extend to these singular metrics. So now I am in the case of a smooth, compact, complex manifold of dimension D, an L-align bundle with a Hermitian metric. Now it's smooth on the whole space. Then I take a rational section of the line bundle. So let's assume that we have a rational section on the line bundle. Then I have the curvature form. The curvature form omega is minus DDC of the logarithm of the norm of S. This is a 1-1 form, which is independent of the section. Because if I multiply the section by a holomorphic function, then it will be killed by DDC. It will be harmonic. Now, this norm is called semi-positive if and only if this curvature form is positive. And positive for curvature forms means that whenever I have a small holomorphic disk, the integral on this small holomorphic disk of omega is always bigger or equal than 0. Okay? So this will be the definition of being semi-positive or PSH for a metric. Then, if I have a line bundle with a semi-positive metric, it turns out that it needs to be ample, and then I can define the volume of L as the limit when L goes to infinity of the dimension of the global sections of the line bundle of powers of the line bundle, and then I normalize with this. And then the theorem of, so the theory of Chern-Weil and the theorem of Hilbert Samuel tells me that these three quantities are the same. So I can look at the volume of the line bundle, which is something in some sense very algebraic. It's just telling me about this graded ring and telling me how the piece of the graded ring grows. I can look at the divisor of the section S. This is a geometric object, and I can take the intersection of this object. This is a very algebrogeometric object. It's just an intersection product of divisors. Or I can just look at the integral along X of the curvature form to the power D, which is a completely differential geometry, differential object. And these three objects are the same. So this is the typical nice theorem that relates algebraic quantities with differential geometry quantities. And then the question is, okay, this is very nice when the metric is smooth, but what happens if the metric is singular? So can we get something similar for singular metrics, or at least for some kind of singular metrics? Okay, so now is where we need to relate three actors. One will be B divisors, the other will be graded linear series, and the third will be plurisodharmonic metrics on line bundles in the toroidal setting. So let's start with toroidal B divisors. Now assume that I have X a complex variety and B a fixed boundary divisor that I will assume that is a simple normal crossing divisor. Then the complement, so X minus B will be a quasi-projective variety if X is projective. And then to this normal crossing divisor, I can associate a fan, which is the conical polyhedral complex associated to this object. And an example has appeared already in the talk by Kris, because, so for instance, if X is just P1 and my divisor B is just 3 points, then this conical polyhedral complex will be this picture that we have seen in his picture. So this is just the dual complex of the simple normal crossing divisor. Now I can look at the divisors on X that are supported on B, and I will write by dxB the set of all Cartier R divisors, so I allow R coefficients on X with support on B. And I will write R of XB, what is the allowable modifications of XB. So this means that modifications are birational transformations of X, but I only want to look at toroidal modifications, in the sense that if I have, for instance, a normal crossing divisor like this, that will correspond to the delta will be just a cone of dimension 2, then I can blow up this point. So if I blow up this point, this is allowed, and this will correspond just to subdivide my cone complex. But if I take a point here, I am not allowed to blow up this point outside, because if I blow up this point, I will get another cone that is different. So I only want to be able to blow up at toroidal points, at toroidal subvarieties. And this corresponds, so these are completely described by rational subdivisions of this polyhedral complex. So for every rational subdivision of my fan, I will get an allowable modification. An allowable modification is just a rational subdivision. So it's a very combinatorial object. And now I want to define the B divisors. So they come in two flavors. So some kind of a finite B divisor, so I can define the B Cartier divisors as the direct limit for all possible toroidal modifications of the divisors on XP BP. What are these? So a divisor with support on B is described by a piecewise linear function on the skeleton, on this polyhedral function delta. And then this direct limit will be described by piecewise linear functions on delta in an arbitrary subdivision, in a rational subdivision. So I need to ask that the rational fan of the function has to be rational. But I can do another limit. Instead of looking at the direct limit, I can look at the inverse limit, because every time I have a modification, I have a push forward of divisors. And using the push forward of divisors, I can look at the inverse limit for all possible divisors on all possible models. And it turns out that this inverse limit corresponds to arbitrary conical functions on the rational points of my polyhedra. Completely arbitrary, completely discontinuous, any function you can imagine, conical function, will give an element of this inverse limit. Okay? So, in particular, a Cartier B-divisor is just you go to a finite, but maybe very big, but finite modification, and then will be a divisor in this finite modification. While a Weil B-divisor will be a collection that keeps changing in every modification. So I will need a collection d pi for every modification, but I need that they are compatible in the sense that if I have a map of modification that will be a blow up, I need that the direct image of dp is just dp prime is just dp. So yes?
Only consider toroidal modifications.
Yes, here I am only considering toroidal modifications because then I can read everything on the skeleton. This is why I can use tropical geometry because everything will be, in some sense, written in the skeleton. While if I take arbitrary modifications, I will need to go to the Berkovich space, and then things will be more difficult to look at.
Do this toroidal modification dominate other?
No. So they are very, very few. In the sense that, look, so you have the whole Berkovich space, and here this will be a skeleton, a small piece on the Berkovich space, and then the toroidal modifications will be looking at just subdivisions on this fixed skeleton. So it's something which is very controlled because you are in a fixed skeleton. Well, if you start blowing up other parts, then your skeleton will start growing and going to all things, and at the end you will need to look at the whole. So going toroidal is just that you want to keep in your skeleton and don't move from the initial skeleton. Okay? Of course, there is also a non-toroidal version, and where you allow all possible modifications, but then you will need to use refinement techniques. Okay. Now, as I was saying, Weil B-divisors are very complicated because you have all possible conical functions, but we can add the condition of being nef, so some positive condition. This will help us a little bit. So the B-divisors, both Cartier and Weil, they are limit of finite dimensional vector spaces, so they have a topology. We have an inclusion of the divisors on a model inside the B Cartier and all of them inside the Weil B-divisors. Now I can look at the nef divisors on a particular model, and then the nef B-divisors will be just the union, so the closure of Cartier nef divisors. Okay? Now a theorem that we prove with Anna. So now imagine that you want to do intersection theory on B-divisors. Of course, if you have Cartier B-divisors, it's very easy because you go to a model where all of them are defined, and then you can make the product of B-divisors. Now imagine that you have n B-divisors, n minus 1 of them are Cartier, and one of them is Weil. Still you can make the product because you can use the projection formula to see that the product exists. But you cannot multiply arbitrary B-divisors, Weil B-divisors. But if they are nef, then one can prove that the intersection product extends to all nef B-divisors. So there is a nice intersection theory for Weil B-divisors. So with Anna we prove this in the toroidal case, and Dan and Fabre prove it in the general case. So really for nef B-divisors there is an intersection theory of B-divisors. Okay. Now this was the first actor. The second actor are graded linear series. That this should remind you a little bit about, for instance, the theory of Okunko bodies. So I have now a complex variety, F the field of rational functions. Then a graded linear series is just a graded subalgebra of the polynomial rings, the polynomials on F. And if L inside F is a finite dimensional subspace, then AL will be just the subalgebra generated by L times T. So I put L in degree 1, and then I look at the subalgebra generated by L. And I will say that A is of integral type if it is so if there exists an L, such that AL is contained in A, and A is finite over AL. And I will say that A is of almost integral type if it is contained in B, and B is of integral type. So these are conditions of, in some sense, finiteness conditions. That, for instance, they are the conditions that are needed to define Okunko bodies related to this graded linear series. And I will denote my algebra A will be a sum of graded pieces, AL. And the classical example, if I have a divisor on X, I can look at the linear series associated to this divisor. So L of D will be all the functions on the field such that the divisor of f plus d is effective. And I have to add the 0. And then I can define Rd just as the direct sum of L of LD, so of a multiple of D, and then I put the T to the L just to keep track of the degree. Okay, so these are the linear series. And in the case where D is a divisor, then I get that Rd is of almost integral type. Okay, now we go to the toroidal singular Hermitian metrics. So what are toroidal singular Hermitian metrics? Again, I have a complex manifold, B a simple normal crossing divisor, U is the complement, L a line bundle on X, and then I have a singular metric, will be called a PSH toroidal metric with respect to the boundary divisor, if first it is continuous on U, so it is continuous on the complement of the boundary divisor. Now, if I have an open trivializing set and S a generating section of L, then I can look at the function f, which is minus log of the norm of S. Then I want that this function is plurisobharmonic, which means that it can have the value minus infinity, so it can be singular, but it has to be upper semi-continuous and locally integrable. And once it is locally integrable, I can take the derivative, the second derivative, ddc of f, in the sense of currents, and I want that this is a positive current. Okay, so this is a being positive. And then the condition of being toroidal is that if B is a coordinate neighborhood, such that my normal crossing divisor is given by set 1 up to set k equal to 0, then I want that the function f has to be a function g of the logarithm of the first variable up to the logarithm of the last variable plus something which is locally bounded. So that in some sense the singularity can be expressed just in terms of the logarithm of the norm of the coordinates. Okay? So this is the main singular part, this is locally bounded, so in some sense it's not singular part. And if we add the condition of being PSH, then this function g has to be convex. It will always be convex if my function f is PSH. Okay? Now I want to see the interplay between these three actors, the singular metrics, the graded linear series, and the B-divisors. So how we go from toroidal PSH metrics to B-divisors? Well, this can be done in a completely analytic way using what is called the long numbers. But in the toroidal case, if the metric is PSH and toroidal, I get a divisor that is NEF, and the difference between the algebraic divisor of S and this divisor that I can define using the metric, this difference will be a toroidal B-divisor, as I have defined previously. And this toroidal B-divisor will correspond to a conic function, phi of d on this conical complex. And what is this function? This function can be read directly from the metric. So if I can write down the log of the section as this function g that codifies the singularities, and this part eta that is the locally bounded, then the function phi of the divisor d, restricted to the cone corresponding to this strata, is what is called the recession function of g, which is in some sense you take your g, it's a convex function. You can linearize the convex function just as taking the limit when lambda goes to infinity of minus 1 over lambda times g of lambda x, and this will be the function of the divisor. So there is a very explicit construction using just the shape of the singularity. Okay. Now we can go from graded linear series to B-divisors and back. How this works? Well, this is just copying a little bit what we have done for line bundles, but adding the information of the metric. So if I start with a graded linear series, then I can construct a B-divisor as looking at all possible divisors such that LE plus the divisor of F is effective, and then taking the infimum of these objects, and this will define for me a B-divisor A that depends only on the graded linear series. In general, if I take any graded linear series, this B-divisor will not necessarily be toroidal. Or if I start with a B-divisor, I can look at the F in F such that d of pi plus the divisor of F is effective on on all the models, and then I can take the graded linear series as just the sum of all these of all these degrees. So I can go from B divisors to graded linear series and from graded linear series to B divisors.
So
Yes?
question.
Yes?
Where is the information of the metric?
No, sorry, here there is no metric. Next, so the metric will come here. The metric will come here, sorry. Yes. So now I have my line bundle, now with a metric, and then the information of the metric is that I will look at all functions on f such that the norm of f times s is bounded. So this will be the linear graded series. So the linear graded series will be associated to a line bundle, a metric, and a concrete section, so to get a divisor. And then R will be just the sum of all of them. Now, these objects, in some sense, they have compatibilities, and the compatibilities are as follows. So if a divisor is smaller than another divisor, then the graded linear series will be contained. If the graded linear series are contained, then the divisors will also satisfy this homogeneous condition. Until what time do you have? 5 minutes only? Okay. Well, then if I start with a B divisor, look at the graded linear series and take again the B divisor, I don't get the same one I started with, I get something which is smaller. If I start with a graded linear series, took the B divisor, take then again the graded linear series, I get something which is smaller, not necessarily equal. I get also that if I start with a line bundle with a metric and I go to the graded linear series, they will be smaller than going through a B divisor. So it's not true that I can go directly. But in the toroidal case, I get a sandwich. So I get that the graded linear series associated to the line bundle is contained in the graded linear series associated to the B divisor. But if I perturb the B divisor slightly by something in the boundary, then I get the other inclusion. So they are not the same, but they are almost the same. Now, some properties. So I will say that a Weil B divisor, then I can define the volume as the dimension, the growth, the asymptotic growth of the graded linear series, and I will say that D is big if the volume is strictly bigger than 0. And then with Anna Botero, Holmes, and de Jong, we prove that if D is big and Neff and toroidal, then if I start with a B divisor, go to the graded linear series and take back the B divisor, then I get the same object. And corollary is that if I get a line bundle with a singular toroidal PSH metric, if I go to the B divisor, so as the B divisor is big, then the B divisor associated to the graded linear series is the same as going directly to the B divisor. Okay? And now another theorem that is easy to prove is that if A is a finitely generated graded linear series, and I look at the B divisor associated to this graded linear series, then it is a Cartier B divisor. And if it is a Cartier B divisor, the associated function will be piecewise linear. Okay? Hence, the phi d will be piecewise linear. Now, we can extend Chern-Weil theory and Hilbert Samuel to this setting, in the sense that if I have this line bundle with a singular PSH toroidal metric, and I assume that the metric is smooth on U, which is the case for us in the case of line bundle of Jacobi forms, then the volume of the associated graded linear series is always equal to the integral of the curvature on the open. So in particular, I am saying that this integral is convergent, and it is also equal to the intersection product, but the intersection product has B divisors, as Weil B divisors. Okay? And there is a recent paper by Xia that extends this result not only for line bundles, but to vector bundles using Segre classes. And now let's apply this to the algebra of Jacobi forms. So the first result we can obtain is that it is not finitely generated. And it is not finitely generated because, so we know by the theorem I commented by Ziegler, that an holomorphic section is a Cusp-Siegel form if and only if the norm is bounded. So the Cusp forms are exactly the graded linear series associated to the metric. Okay? Now, the B divisor associated to the Cusp forms is exactly the same as the B divisor associated to all forms, because in some sense they differ very little. And then the B divisor associated to all the forms is exactly the same as the B divisor associated to the line bundle with the metric. But we know what is the function associated to to the metric. So from the metric, we can read explicitly what is the associated function. And the associated function is not piecewise linear. Hence, this divisor is not Carty divisor. Hence, this algebra cannot be finitely generated. Okay, so we really obtain that the algebra cannot be really generated. And this is not a Cartier B divisor. And hence, this is not finitely generated. Well, we can, here is a little bit how one computes, but we can skip this part. But then for the asymptotic dimensions, we can use now that the lim sup of these dimensions can be computed as an intersection product and can be computed as the integral of this form. And now, again, this integral can be computed explicitly once one uses Siegel formula for the volume of the modular variety, and we can recover Thijs' formula just from this. Okay, thank you very much.